Welcome to this lecture number 13 on NPTEL course on fluid mechanics for undergraduate students in chemical engineering. The topic that we are currently discussing is under the title of macroscopic balances, or they are also referred to as integral balances. Just to remind you of what we were discussing in the last lecture, macroscopic balances are concerned with entire equipment, process equipment like pumps, compressors or tubes, networks of tubes and so on. So, we are going to apply the principles of conservation of mass, momentum and energy to control volume, what is called a control volume. A control volume is any fixed region in space that is of interest to us. So, you could have, for example, a pipe leading to a pump, and then there could be several other pumps also. So, all this could come under a single control volume, okay, depending on the nature of the application. This is just an example. Of course, the context in which the problem arises will suggest control volume by itself, and it comes from some experience by solving various problems in fluid mechanics. One learns how to choose appropriate control volumes that is convenient to a given problem. But nonetheless, in general, a control volume is a region in space that is of interest to us, in which we want to compute certain quantities such as forces or power requirement in pumps or and so on, similar quantities. Okay. So, whenever you have a control volume, we have this instrument, or we have this tool called the Reynolds transport theorem. Which relates the rate of change of quantity in a system. So, just to remind you, a control volume is a fixed region in space. Here I am denoting the control volume by blue line. A system is that fluid that occupies the CV at a given time t, but at a time immediately later t plus delta t, the system has moved slightly away from the CV. A system or a material volume contains the same set of material points. There is the same set of fluid particles. So, you are following the same set of fluid particles, while a CV is a fixed region in space. Okay. So, the Reynolds transport theorem tells you that suppose you have a CV, and at a time t plus delta t, the system has moved slightly away. So, this is time t, this t plus delta t. What is the rate of change of various quantities that are present in the system, okay, at time t, as a function of in terms of the variables that are expressed in terms of the control volume. So, the system rate of change of any quantity. So, we introduced a general quantity called eta, which is per quantity per unit mass. This quantity could be mass, momentum or energy integrated over volume, is d dt over CV eta rho dV, the time rate of change of that quantity present in the CV, okay, plus a flux contribution, which is over the various inlets and exits of the CV, eta rho v dot n dA, okay, where n is the unit outward normal to the control surface. Okay. And this is the Reynolds transport theorem. This is the left side of the Reynolds transport theorem. Okay. Let me just write in words, is the rate of change of any extensive quantity such as mass, momentum or energy present in the control mass or system at time t. Okay. The system and control volume coincide at time t, but at a slightly later time t plus delta t, the control mass would have moved away from the CV, because if you follow fluid particles, by virtue of law all these particles will be moving slightly away. Okay. So, that is the idea. And the right side, the first term on the right side contains the rate of change of that quantity present in the CV itself. So, there are two contributions to the rate of change of this quantity extensive quantity as you follow the system. One is because of the fact that there is an inherent rate of change present in the CV itself. This is a rate of change in the CV, and things could also change because of the fact that fluid is moving in and out. By virtue of this flow in and out of the CV, there are fluxes of quantities inside and outside the CV, and that is this quantity. So, this is the flux term. So, this is a flux of quantity, okay, moving in or out of the CV. As CV is visible to the outer surface through the control surface, so through the surface, the control surface. Okay. So, the interpretation of various terms is as follows. So, just to remind you, eta is any quantity per unit mass times rho, which is density, which is mass per unit volume. This product will give you any quantity per unit volume in a tiny volume in a system. Integrated over a entire volume will give you the total amount of mass, momentum or energy that is present in the system, and this is d dt of that, the time rate of change of any quantity. The same interpretation, but here instead of integrating over the system, which is a function of time, we are integrating over a CV, which is fixed region in space, and this is the flux term. The interpretation is as follows: V dot n is a normal component of the velocity at the control surface, times dA is the normal volumetric flow rate, okay, of the fluid, times density is the mass flow rate, times the quantity per unit mass will give you the rate at which any quantity such as mass, momentum or energy is entering or leaving the CV through the control surface. V dot n is positive if there is if the fluid is leaving, because n is a unit outward normal to the CV. So, V dot n is positive if fluid is leaving, okay, if fluid is leaving, and it is negative if fluid is entering the CV, entering the CV. Okay. So, that is the general Reynolds transport theorem. We next applied it to the case of conservation of mass, the principle of conservation of mass. So, this is the integral balance for mass conservation. Suppose you have an arbitrary CV, okay, and in reality you may think of this as a container with several inlets and exits, okay, that is how it will appear in a real problem. Okay. So, fluid may enter through certain entries and exit through certain exits. Okay. So, this is the CV. Okay. So, you identify the CV. What is the how does the conservation of mass principle work for this? So, eta is quantity per unit mass. Now, the stuff that we are interested in, the quantity that we are interested in is mass itself. So, its mass per unit mass is unity. So, we have to substitute 1 in the Reynolds transport theorem. So, d dt of rho dV of the system, okay, is d dt of V control volume over the CV rho dV plus integral rho V dot n dA over the control surface. This is by applying Reynolds transport theorem with eta equals 1. Now, the conservation of mass principle says that if you follow the same set of mass points, the mass is neither created nor destroyed. So, this is 0 by law of conservation of mass Okay. If you follow the same set of mass points or fluid particles, since mass can neither be created nor be destroyed, if you follow the same set of mass particles, fluid particles, their mass will remain a constant. So, that is the meaning of this derivative, where you are following a system. That is, by system we mean that you have the system is like this at time t equal to t, at any time t, at a little time later the system will deform, but it will have the same set of mass points as it had at t. So, if you follow the system at a later time at t plus delta t, the mass will remain the same. So, the time rate of change of mass of the system is 0. So, the mass conservation principle as applied to a CV reduces to d dt of integral over CV rho dV plus integral Cs rho V dot n dA is 0. Okay. because this term is 0. So, this right side must be equal to 0. Now, I can interpret this in the following manner. I can take the flux term to the other side, Cs rho V dot n dA. Okay. Now, the physical interpretation for this is the rho times dV is the mass that is present in a tiny pocket, tiny volume in a CV. Integrated over the entire CV will give you the total mass. This is the rate of change of mass present in the CV. Mass in the CV. Now, why should the mass in the CV change? Well, it changes because there are entry and exits to this CV, okay, and through the entry and exit fluid is flowing in and out, and if there is a net flow in, then there is an increase of mass. If there is a net flow out, then there is a decrease of mass. So, what is the right side? V dot n is the volume, V dot n is the normal component of the velocity, times dA is the volumetric flow rate, okay, over a tiny part of the control surface. So, if you look at a control volume like this, okay, then if you take a tiny area dA, the net volumetric flow rate is V dot n dA. Okay. Now, times rho will be the net mass flow rate, integrated over the entire surface will give you the total net mass flow rate in or out of the system. Now, V dot n is positive if there is a net flow out. If there is net flow out everywhere on the control surface, then this integral will be positive. Negative of a positive quantity is negative, that means that there will be a decrease of mass with respect to time in the CV. If V dot n is negative through every part of the control surface, then there is a net inflow because n is the unit outward normal. If V is coming into the CV, V dot n will be negative if there is inflow, and V dot n is positive if there is outflow. Okay. If V dot n is negative, then negative of negative is positive. So, this leads to a buildup of mass, that is d dt of mass in the CV is positive. Okay. So, this is the most general form of mass conservation principle, that d dt of integral over CV rho dV is minus integral over Cs, okay, minus integral over Cs rho V dot n dA. Okay. Now, we can also simplify this to many special cases. This is the most general form of mass conservation that is valid for any system in fluid mechanics, any problem in fluid mechanics. Now, for some special cases, the first special case we did is for the case of incompressible fluids. When the fluid is incompressible, rho is a constant, rho is independent, rho does not change with pressure. Whenever there is a fluid flow, there are pressure changes associated with any flow, but if the density changes are small or negligible, then we can treat the density to be constant with respect to variations in pressure. Such fluids are called incompressible fluids. Okay. If rho is a constant, then you can pull rho outside the integral. So, d dt integral, sorry, this is CV rho dV, okay, is again rho is constant, V dot n dA. Now, since rho is there in both sides of the equation, it cancels out. Now, sorry, there is no rho here. Now, integral over dV of the CV is nothing but d dt of the CV itself, the volume of the control volume. Now, the control volume is fixed region in space, it is constant, so it is 0, it does not vary with time. So, minus integral Cs V dot n dA is 0. Okay. Now, let us apply it to a case where you have typically a CV can be a container with a region of interest with several inlets and several outlets. Okay. There can be several inlets I and several outlets. Okay. Just schematically, okay, fluid can come in and go out through several outlets. Okay. Now, I can therefore split this this flux term. Okay. So, for an incompressible fluid, V dot n dA is 0. This is the conservation of mass principle. This is a simplified form for incompressible fluids. Okay, rho is constant. Now, the control surface is split into various control surfaces, CS1, okay, plus CS2 plus so on is 0, okay, because there are typically several countable number of inputs and outputs in generally in any realistic problem in fluid mechanics. In such a case you can write like this. Now you can also demarcate inlets and outlets. So for an inlet, V dot n is negative inlet and V dot n is greater than 0 for an outlet, because whenever you have a control surface, okay, suppose you have a conduit, okay, if this is the n is the unit outward normal, if V is opposite, then V is entering in, V dot n is negative. If V is leaving, so in out, okay. If V is leaving, fluid is leaving the control volume through the control surface, V dot n is positive. So we can split this into various inlets. So since V dot n is negative, let us call V dot n as V, okay, and the magnitude of V dot n is V, okay, and the sign of V dot n is negative for inlets and positive for outlets, okay. So V I, okay. Now usually what happens is that, so let us just write it like a vector. So okay, let us just write it like a vector, summation, okay, over various inlets and outlets. Now if the flow is uniform, that is the velocity, we have in general terms like this CS1 V dot n dA. Now we can choose velocity to be completely normal to the CV, either it is entering or leaving. We can choose our control surface such that the velocity is normal. So V dot n is essentially, okay, some V, okay, V dot n is the normal component of the velocity, that is V, okay, and then there is a sign associated with it. So if it is an inlet, we will put a negative sign, okay, and this is for all the inlets, okay, minus summation over all the inlets plus summation over, so let I denote all the indices for inlets, and similarly for summation over all outlets is 0, okay. So in general we have V I dAI summation over all inlets is integral summation over all outlets V I dAI, okay. Now if the velocity is uniform, if the flow is uniform, then the velocity vector is independent of the cross section of the control surface. The velocity vector is a constant, uniform flow. Usually flow is not uniform in flow through tubes and channels, as we will see later, but if the flow is like a free jet that is going in an atmosphere, that is moving in atmosphere in air, then you can reasonably think of it as an uniform flow. So as a matter of convenience, in many simplified settings, one may think of the flow to be uniform. In such cases, V is independent of A, of dA. So you can pull it out, and integral over dA over the control surface is simply A. So summation over all inlets VIAI is summation over all outlets VIAI, okay. If there is only single inlet, single outlet, single output, then V in A in is V out A out, okay. This is a very simple form of conservation of mass applied to incompressible flows. Whether it is steady or not, it is not a problem, because as CV is a fixed region in space, this is valid for both steady and unsteady flows as long as the flow is incompressible, okay. So if the flow is uniform, then it that is the velocity vector is independent of the cross sectional area, then this is the simplified form of mass conservation equation. V times A is the volumetric flow rate Q, so Q in is Q out, okay. So generally if you have a single input single output problem, mass in must be equal to mass out, because the fluid since the fluid density is constant, that means that the volume rate at which volume is flowing in is equal to rate at which mass is volume is flowing out, okay. This is denoted by volumetric flow rate is denoted by the symbol Q dot, okay. So this is the simplified form of mass conservation equation that is useful in many contexts and practical applications, okay. Now you can also consider another approximation, that is the steady flow approximation. When the flow is steady, d dt is 0. Okay. Whether the fluid is incompressible or not is not a matter. Okay. We are merely considering steady flow, that is d dt is 0. When d dt of any quantity is 0, so we have the general mass conservation equation rho dV over the Cv is minus integral over Cs rho v dot n dA. Now, for steady flow approximation, d dt is 0, valid for both incompressible and compressible fluids. Okay. So, this is independent of whether rho is constant or not, because we are assuming the flow to be steady. So, here integral over Cs. Now, since rho is not a constant, we have to keep rho inside the integral is 0. Okay. And if the flow is uniform and you assume inlets and outlets that are discrete in number, okay, then you can write this as summation over v dot a I over all inlets is equal to summation over rho I v I dot a I over all outlets. Okay. So, this is the simplified form of mass conservation equation for steady flows. Okay. And if the flow is uniform, then v dot a will be simply, okay. So, this is simply so this is still without taking into account the sign convention for inlets and outlets. So, v dot a is v a for outlets and v dot a is minus v a for inlets. Then we can take one of these out and write v rho I v I a I over inlets is rho I v I a I. Okay. So, this is a simplified form of mass conservation equation for valid only for steady flows, and density can vary from inlet to outlet. Although the form appears fairly similar to what we had before for incompressible flows, there the equation that we derived was valid whether the flow is steady or not. Here it is valid only for steady flows. Okay. Now, I told you a thing about uniform flow approximation. We will come to this a little later when we do differential balances, but let me just tell you what will happen in reality. Suppose you have a flow in the x direction, let us say in a rectangular channel that is extending in the z direction that is coming out of the board in the z direction, the flow is in the x direction. Okay. Now, if you have flow between two rigid plates, okay, then the velocity in the fluid will in general be non-uniform, that is the velocity will be 0 at the walls and it will be maximum at the center. So, and this is called a velocity profile, it is called a velocity profile, and in general therefore, one cannot pull the velocity if whenever you have v dot n dA, you cannot pull v out, because velocity is a function of the coordinate with which you are integrating. Okay. So, one has to do this integration in general. Okay. So, for example, in a channel flow in a rectangular channel, the velocity in the x direction is a function of the y coordinate in the following manner. It is the maximum velocity which is at the center, this is called v max, times 1 minus y by b. Suppose this is the 2b, okay, and the y coordinate is set like this, then whole square. Okay. Then if you want to integrate integral v dot dA, what this would mean is, suppose fluid is entering, okay, in the x direction, the unit outward normal is, or let us keep the exit for simplicity. Suppose fluid is exiting the channel in the x direction and the unit outward normal is also in the I direction, that is along the x direction. Okay. Then v dot dA will be simply v dot, okay, dA is simply dy times W I, where W is the width of the channel in the third direction. Okay. The channel is also wider in the direction perpendicular to the board. Okay. So, this will simply give you V dot I is simply, and W is a constant, can be pulled over, it is V x times dy, okay, and integrated from y equals minus b to y equals plus b. This is the meaning of this term V dot dA. Okay. So, this is W times y equals minus b to plus b, okay, times V x of y is V max times 1 minus y by b square. Okay. So, this is the meaning of integral V dot dA in general for a non-uniform flow, and this is nothing but the volumetric flow rate in the channel. Flow rate. So, if you want to calculate the volumetric flow rate, this is how one calculates, and to get a definition of an average velocity in the channel V bar, it is defined as the volumetric flow rate divided by the cross sectional area. So, this is Q dot divided by the cross sectional area of the channel is nothing but 2b times W. Okay. The width, the whole width of the channel is, the gap of the channel is 2b, and the width out of the paper is W. So, 2b times W is the width of the channel. So, this one calculates or defines average velocity by taking or computing the volumetric flow rate for a non-uniform flow and dividing with the area. Suppose the flow is uniform. If you have uniform flow, then V x is independent of y, the normal coordinate. So, integral V dot dA will be some constant u, okay, times. So, let us just do it. So, if V is simply a constant in the x direction, so you will have u I dot dA is nothing but dy W I. Okay. So, this is nothing but integral u dy and y going from minus b to b. Okay. This is nothing but u times 2b times W. This is the volumetric flow rate. The average velocity is Q dot divided by area, cross section area, that is nothing but Q dot divided by 2b times W, that is equal to u times 2b times W from this expression divided by 2b times W. Okay. So, the 2dW 2bW cancels, implying that the average velocity is the uniform velocity. That makes physical sense, because if the velocity is constant independent of the cross sectional coordinate, then the independent of the coordinate perpendicular to the direction of the flow, then obviously even if you average it, it will give you a constant answer. Okay. So, this is the meaning of this particular quantity called average velocity. Okay. So, this completes our discussion on mass conservation. So, that really completes the discussion on mass conservation, and we will apply mass conservation is so important that in any problem that involves other balances such as momentum balance or energy balance, we will see a little later when we apply these principles that mass conservation will give you one input to the problem, that is, it will give you one equation to relate various unknowns with. So, mass conservation is always satisfied. So, it must be always satisfied in any problem in fluid mechanics. So, the integral form of mass balance, we will see a little later, is also always applied. In some very rare cases, it gives you a very trivial consequence, but mostly it gives you a useful information in terms of relating the unknown variables that we want to solve for. Okay. The next in our topic in momentum in integral balances is the integral momentum balance. Integral momentum balance applied to a CV, as applied to a CV. We want to derive an integral balance for momentum, okay, as applied to a control volume, but we have to go back to the control mass approach, because really speaking the momentum balance rests on Newton's second law of motion, which says that the sum of forces acting on sum of all forces acting on a body. A body is an identifiable piece of matter, okay, in space. Sum of all forces acting on a body is equal to, okay, the rate of change of the time rate of change of momentum that is present in the body, which is the system. That is, you follow the same set of mass points. Okay. The time rate of change of momentum of all these mass points which form this system or a control mass is equal to sum of all the forces that are exerted by the surroundings on the control mass. Okay. So, the Newton's second law is really applied to a control mass. Okay. It applies only for a control mass or a system control mass and not directly applicable for CV. So, we have to use Reynolds transport theorem to simplify the time rate of change of momentum that is present in the system and relate it to variables in a CV. This has been our strategy even in the conservation of mass principle, but there it was very straightforward because the time rate of change of mass of a system was 0, because if you follow the same set of mass points, then its mass will not change as per conservation of conservation of mass principle. So, therefore, that was simple, but here it is slightly more involved, as we will see. Okay. So, the total momentum that is present in a system which is identical to the CV at time t is equal to volume or integrated over the volume of the system, rho times velocity times dV. Okay. Mass times velocity vector is momentum vector, momentum is a vector, mass times velocity vector is momentum vector. In a fluid, density can in general change from point to point. So, if you take a tiny volume, then density times velocity is the momentum per unit volume times the tiny volume will give you the differential volume will give you the momentum present in that volume, integrated over the entire volume of the system will give you the total momentum that is present in the system. Okay. And since we want d dt, we will put d dt, and this must be simplified, this must be use Reynolds transport theorem to simplify this. We will do this shortly. Okay. The sum of all the forces is sum of body forces and surface forces. Okay. So, surface forces on the CV, suppose you have a CV, the system coincides with the CV at time t. What are the various forces that are being acted upon by the fluid or other solids that are present outside on the CV, on the surface of the CV, and then there are body forces like gravity which act through the entire volume of the CV. So, which coincides with the system at that time. So, these are the various forces that are acting on the system. Okay. So, let us apply the Reynolds transport theorem. The Reynolds transport theorem, if you recall, the Reynolds transport theorem is d dt of integral over volume of the system eta rho dV is nothing but d dt of integral over the CV eta rho dV plus integral over Cs eta rho v dot n dA. Okay. Now, we want conservation of momentum. So, eta is momentum per unit mass. Okay. So, eta will be mass times velocity divided by mass. So, mass cancels. So, eta will be simply the velocity vector itself. So, the Reynolds transport theorem as applied to the momentum conservation principle is V dV is d dt over the CV rho v dV plus integral over Cs rho v dot n dA. V dot n dA is sum of all surface forces plus sum of all body forces. Now, if you recall, the system and the CV, they coincide at a given time in the application of Reynolds transport theorem. Okay. So, the system and CV coincide. So, Fs and Sb are merely the forces acting on the CV, because they are originally the forces acting on the system at time t, but since the system and CV coincide at time t, so these are merely the forces acting on the CV themselves. So, we are now able to obtain a version of the Newton's second law to variables that pertain to a control volume. Okay. So, essentially what we have is this F S plus F B, the sum of all surface and body forces, is equal to integral rho V, sorry this is yeah, it's okay, dV plus integral control surface rho V V dot n dA. So, this is the general form of integral momentum balance. Okay. Now, we can simplify it to some special cases. Suppose you have limiting cases. You have uniform flow. When the flow is uniform, then V vector is independent of dA. So, you can pull it out of the area integral in the surface term. So, you get F is F s plus F b, sum of all forces on the CV is d dt, okay, rho V dV plus summation over C s V rho V dot A. Okay. Still there is a sign associated with area, well, let us just put it as V dot n A, because if the flow is entering the CV, then n is unit outward. So, V dot n is negative, and if the flow is leaving, then V dot n is positive. Okay. So, that is the usual convention that we follow. Okay. Usually what happens is the body force is due to gravity. So, the body force is merely integral over CV rho g dV. Okay. Now, what are the various causes of surface force F s? These are the surface forces acting on the CV. Okay. Suppose you have a system like this, okay, and this is our CV. The red line is the control surface of the CV. Okay. So, this is our CV, the red line is our CV, okay, and fluid is entering, let us say like this and going like this. Now, on the surface is the control surface can be divided into two parts, a part where flow is entering and the part where flow is leaving. This is one part where there is entry and exit, and there are the stationary parts here. These are stationary parts where of the CS where there is no fluid entry or exit. Okay. So, various forces can act on the surfaces. For example, here whenever there is flow, suppose I just exaggerate this entry, okay, whenever fluid is entering control surface into the CV, then there are pressure forces that act on the control surface. Okay. So, that forms a force, and whenever there is fluid flow, okay, inside a CV also, at the surface itself there can be resisting forces due to the shear stresses exerted by the wall on the fluid. Okay. So, both these forces, surface forces, are in fact possible. Okay. But many a times in simple problems we neglect in many cases, in many examples, it turns out that we neglect shear stresses and retain only the pressure forces. One has to look into the context and then make a more judicious decision on whether shear stresses are in fact negligible or not, but in most cases it turns out that one can get a rough answer by neglecting shear stresses, just because of the fact that we do not have much idea about the drag forces that are exerted by the solid surfaces on the fluid. So, we merely neglect them, but while doing examples I will try to indicate where one can actually get an estimate and so on, but right now we retain only pressure. Okay. So, the pressure, suppose you have a CV and this is the unit outward normal, the pressure acts in the direction of minus n. Pressure is a surface force, but it acts, it is compressive in nature. So, Fs is integral over Cs minus P dA. Okay. This is minus okay. So, that is the way you you compute the surface force due to pressure on the control surface. Okay. So, what is important here when calculating the surface force due to pressure? Suppose you have an entry and suppose you have an exit. This is your CV, let us say. Okay. In the entry, the pressure, the outward unit normal to the flow is n, while in the exit it is in the direction of flow. Okay. The flow is exiting like this while it is entering like this. So, what is important is that pressure acts in the direction opposite to the normal both here as well as here. So, the pressure here is acting, the pressure forces are acting like this here in the direction of minus n, the pressure forces are acting like this here. So, one should not think that just because the fluid is leaving the CV through this Cs, okay, the pressure forces are in this direction. Whenever a fluid leaves, the fluid just outside the control surface will tend to resist its motion by exerting a pressure. So, regardless of the direction of motion, okay, the pressure is always in the direction opposite to the unit normal. Okay. So, that is the key thing. One should not apply a wrong intuition that since the fluid is flowing out, the pressure is in this direction. What we are looking at is the force exerted or experienced by the fluid that is leaving out of the CV, okay, by due to the fluid that is just outside, which therefore will be in this direction. Okay. So, this is something that we have to understand. Okay. So, the momentum equation is a vector equation. So, you can write it in terms of three scalar components. The x component will be x component of the body force plus x component of the surface force is d dt of, okay, let me first write the vector form of the momentum equation and then let me so f body plus f vector surface is d dt CV rho v v dot n rho v dv plus Cs rho v v dot n dA. So, the x component of this equation is f b x plus f s x is d dt. So, in this term the only vector is the velocity vector v. So, to take the x component, use velocity vector v has x component u, y component v, z component w. Okay. So, rho u dv. In this term, rho is a scalar, v dot n is a scalar. Even though v is a vector, once you dot it with n, it becomes a scalar. Okay. So, v dot n is a scalar. So, the only vector that is available to you is v, and the x component of it is u, and v dot n remains as such. Okay. So, similarly, the y component of f b y plus f s y is d dt over C v rho v dv plus C s, okay, rho v vector v dot n dA, and the z component is f b z plus f s z is d dt rho w dv plus integral over C s rho w v dot n dA. Okay. So, this is the these are the three components of the momentum balance equation. When you apply the momentum balance equation to any problem, so you will have to refer it to a particular coordinate system, therefore, you will have to solve various components of the momentum balance. So, it is always useful to write it in a component form. Here I have used the Cartesian coordinate system to indicate the various components. Now another thing is to notice the role of pressure on the control surface. Okay. Suppose you have a CV like this, okay, and the unit outward normal is like this, the pressure is in the direction of minus unit outward normal. Okay. Now, so F pressure is integral P times minus N dA. Okay. Suppose if there is a uniform atmospheric pressure acting everywhere, if P is constant, let us say it is due to atmospheric pressure. In many applications you will find that your CV is surrounded by atmospheric pressure, and if that is the only pressure that is acting on the CV, okay, if there is no other pressure that is acting, then P is constant. So, Fp is, so since P is constant you can pull it out, okay, minus also let me pull it out, and dA. Okay. Now, for any closed surface, if you take n like this and integrate it over the surface, okay, it will be identically 0, okay, just by symmetry it has to be 0. So, the net pressure force acting on a CV due to, if the pressure is uniform, is 0, okay, if the pressure is uniform, like an atmospheric pressure. Okay. But in many cases the pressure you will have atmospheric pressure over and above some other pressure. So, the actual pressure force will be due to the difference between the pressure and atmospheric pressure in the direction of minus N dA. This is nothing but the gauge pressure, because P minus Pa is gauge. So, the net pressure force is really because of the fact that there is a difference between the pressure force and the atmospheric pressure. If the only pressure is due to atmospheric pressure, it is completely constant, it is uniform. So, it will give rise to 0. So, the gauge pressure comes naturally when you want to compute the net pressure force contribution on any control surface in a given problem in momentum balance. Okay. So, let me just recap. First of all, some tips, and before I recap momentum balance, some tips in applying the momentum balance. Okay. So, firstly, you choose the CV and CS carefully, such that you can evaluate all the terms in the volume and surface integral easily. Okay. So, one tip is that suppose whenever you have flow, okay, in a direction you choose the CS such that it is normal to the flow, okay, so that V dot n becomes a simple quantity to calculate. Okay. That is one thing. Okay. So, the second point is label carefully each inlet and outlet. Okay. And you must identify all the forces, all the external forces, that is the surface forces, importantly, carefully. Okay. Now, the surface forces, as I told you, is mainly due to pressure, but in some applications you will find that your CV will cut across a solid surface. For example, let us say a fluid jet is impinging on a solid surface. Let us draw the solid surface with blue. Okay. This is a solid surface. and a fluid jet is, let us say, coming and impinging on the solid surface, and let us say it is going like this. Now, let us say you are holding the solid surface in your hand, okay, and we choose the CV to be like this. Okay. So, this is the CV that you are choosing. Let us say fluid layer is leaving, let us say like this, okay, and the CV is the control surface is cutting across your hand. Now, this is the fluid jet that is coming, impinging. Suppose you want to on the solid surface and it is leaving. Okay. Suppose you want to calculate the force exerted by the fluid on the solid surface. Okay. The CV is really cutting through your hand. Okay. You have to include the reaction force exerted by your hand on the solid as a part of external force, external surface force on the CV, because otherwise this CV will not, this solid surface will not remain stationary. Okay. Since the solid surface is remaining stationary, this fluid which is impinging on the solid surface will induce a momentum transfer to the surface, which will have to be resisted by an external force, which is a reaction force from your hand. So, this must be included as a surface force, because there is no other way we can account for this force. This is not a body force, it happens only at the control surface where the CS, the control surface, cuts across your hand. So, that must be incorporated as a surface force. Okay. So, this is something that we will illustrate with the help of an example, okay, in the next lecture. So, we will stop here and we will continue from here in the next lecture by illustrating how the integral momentum balance is applied to compute such forces. Thank you for your attention.